Hello and welcome. We're beginning a new chapter today, chapter 4, but we are still applying the derivative. In this case, we are applying the derivative so that we can analyze functions for maxima and minima. There are different types of maxima and minima that we'll be discussing here, and we'll be primarily looking at this in a graphical sense. So we'll be using the graphs in order to interpret when there is a maximum or there is a minimum. But we'll be doing this with symbolic functions as well. If we can, we'll be interpreting the symbolic functions by use of the graphs, okay, and then geometrically determining where the maxima and minima would be. And in future sections of this chapter, we'll be developing these ideas further so that we can do more complete graphical analysis of symbolic functions and then applying them to real-world type examples and applications. Okay, so that ultimately we want to be able to find optimum values for situations, such as what is the lowest on a cost function, what would be the minimum cost associated with a given level of production, or what is the maximum concentration, okay, of a chemical within a system. Something to that effect, okay, where we want to find maximum and minimum values. Okay, that'll be optimization, and that comes later in the chapter. Okay, on the way, we're developing techniques in order to first to define what is a maximum and what is a minimum, both graphically and symbolically, and we'll be designing techniques to apply calculus, which will allow us to locate these values and define them. We'll be wanting to locate the input values that would target maximum and minimum values. The name we have for the input values where we might find maxima and minima would be called critical numbers. That is, critical numbers are the quantities of x, or the input, or t, whatever the input variable is. Critical numbers is the name we have for those values where we might find a maximum or a minimum. But the value of the maximum or the value of the minimum, if it exists, would be an output, a y value. So for instance, if we're analyzing a revenue function for a business application or finance application, okay, if the revenue is expressed with respect to the number of units that are sold, let's say, if the input is the number of units that are sold, and the output is the revenue, if we were trying to find the maximum, would be trying to find what is the maximum revenue. That is, the goal is to find out what is our highest possible revenue that we could attain over the domain. And the critical numbers in that case would be the possible levels of production. That is, the potential number of units that we would want to sell, which would result in a maximum revenue. Right? So the critical number is associated to a list of input values, which might lead to a maximum or minimum, and then we have to check to see which ones are in fact maxima and minima, or if they aren't either maximum or minimum. Okay? And the output, or the y value in general, is going to be the actual value of a maximum or the value of a minimum when it exists. Okay, so two main types of maxima and minima to talk about here. The first one is called the absolute maximum, or and similarly the absolute minimum as well. Okay, there's an absolute maximum, absolute minimum. They can also be called the global maximum or global minimum, and that can help to recall how the definition of this type of maximum and minima differs from the local or relative maximum and minima that we also want to define. So an absolute or global maximum or an absolute or global minimum would be defined as the value, if it exists, the value of the output variable that is greater than or equal to any other output value that could have been found throughout the domain of the function. Graphical analysis will help us to establish this as an idea. An example of a function that has an absolute maximum, let's say, would be a downward-facing parabola. All right. So let's say we have a parabola opening downward, then the vertex, which has the coordinates hk in general for the vertex of a parabola, right, Well, then the input value h, that would be a critical number. Okay. A critical number of the function. Let's say this is the function y equals f of x. Okay. And k, okay, the output there, the k would be the value that is equal to, we also could say is f of h, in this case, right, is the output of the function, and that would be the absolute maximum. Okay, the absolute maximum of f. That is, the y value that we attain from this point here is greater than or equal to any other y value that we could attain from any other point. So it is the absolute maximum. Now let's take another type of function that attains its maximum more than one time. Like, how about a sine wave, for instance, or a cosine wave? All right, let's say that we have a wave, okay, that keeps returning to the same y value. Okay, so let's say that all of these crests of these waves, let's say they all are at the same height in this case. Okay, I'm going to call that height capital M. Okay, the output at each of these points, M, okay, is the absolute maximum. Okay, the absolute maximum of this function. Let's call this function y equals g of x. So the absolute maximum of g of x. And that absolute maximum is attained in many locations. Let's call, I'll call the input for each of these with C, because we use C for critical number, I guess. That's a good choice. So this would be C1, C2, C3, C4, C5, okay, and perhaps this continues. Now, we need to confirm if this is an absolute maximum, then it has to be that the function doesn't later, at some other value that we can't see, attain a higher value. Like if somewhere, let's say that this were to continue up like this, okay, well then this would become the absolute maximum. The y value here would become the absolute maximum because that y value is now higher than any other y value we could have attained on the graph. Okay, but assuming that this pattern just continues, okay, and that we never reach a y value higher than this, then we have found the absolute maximum, and that would be M. Okay, now, okay, the absolute maximum can be attained in more than one instance. Okay, the definition then symbolically for an absolute maximum is, okay, the absolute maximum is a value that the function actually attains, okay, such that for any other values of x in the domain, the output for any other value of x will never be greater than that value that was attained. Okay, so like in this case here, right, it's just the y value that these points have. Okay, there is no y value we can attain from any other input x that would exceed this y value, right? That would be greater than that y value right there. So the value of the absolute maximum is whatever m is equal to. It's a number, right? It is the maximum value that the function attains. Okay. Similar idea for an absolute minimum, by the way. Okay, an absolute minimum would be attained, right? Graphically, we would say, well, it's the lowest point, or the lowest y value, okay, that the function reaches. Let's say it reaches at these points, and let's assume again that it doesn't at some point out here go lower than this. Under that assumption that, you know, that we're looking at all the possible y values we will get over the entire domain here. Okay, then there are, well, we'd have critical numbers associated with these. I'm going to call these critical numbers here d's. Okay, so this is d1, d2, right, d3. And d4, okay? And then the minimum would be the y value that keeps getting attained at these values right here. Okay, let's call that lowercase m for the minimum. Okay? All right, so we said the absolute maximum is equal to m here. Okay, then I have that all of the ci's, c sub I, okay, are the critical numbers. They're all critical numbers of the function. All right, those are all critical numbers of f, right? So the I is an index. It's a sequence of values. So we have a C1, C2, C3, C4, and C5 in this case. Okay. And now I'm including that lowercase m, okay, is the output, the y value that is an absolute minimum of the function, okay, of g of x, okay, and all the d sub I are also going to show up in the list of critical numbers. Okay. All right. Now, what do we notice that is in common amongst the critical numbers between these two graphs right now? Okay, think about this in terms of derivatives. How do we interpret the derivative when we're looking at a graph? Right? I'll do a different color here. That's a nice one. All right. What would we know about the derivative at, for instance, this point right here? What would we expect it to be? We have a nice smooth curve here, right? A nice smooth curve here, and the derivative right here would look like it would equal 0 because we have a horizontal tangent line. Something to keep in mind. Okay? So let's just notice for right now. Okay? Notice for right now that it looks like, right, f prime of h is equal to 0. Okay. Now over here on this graph, okay, if we take a look at all of these points over here, okay, it also turns out, all right, by the way that I've constructed these functions, we can note this as well, that g prime of all of our critical numbers ci and g prime of all of our critical numbers di, they all happen to equal 0 as well. So we might be able to relate the derivative to the location of the critical numbers. That is, if we take the derivative of a symbolic function and set that derivative equal to 0, we might get ourselves a way of finding some critical numbers that we can then test to see if they might be maximum or minimum values. Okay, if the outputs would be maximum or minimum. Okay, but that's just the start of the process here. Okay, is it possible to create a function that has an absolute maximum where the derivative is not equal to 0? Yes, it is. Okay, how would that be possible? How would it be possible? Right? Yeah. So how would it be possible that we have a y value, okay, that is greater than or equal to any other y value we could attain? Maybe, but where the derivative, okay, for the critical number associated with that y value, where the derivative is not equal to 0. Okay. Let's sketch a function. How about a function that is shaped like this? Okay, where we have a corner or a cusp, okay, at a point. Okay, but the point itself exists. That is, there is a y value at that point, and the y value we get at that point is greater than any other y value we attain here. Okay? Assuming that this doesn't return around, and I'm assuming that it doesn't, otherwise I would include it on this graph. So now the input here, c, that would be a critical number. Okay, it would be a critical number because it is being associated, in this case, it is being associated with one of these maximum and minimum values. Okay, there's more on that in a bit. Okay? But when we talk about what is the derivative going to be at that point, okay, let's call this function, let's call this function k of x, if that's all right. Okay, for y equals k of x, notice now that k prime of c doesn't equal 0, but in fact does not exist. Okay, we have m, which is k of c, okay, that is an absolute max, okay, an absolute max of the function k, and c is a critical number, okay, is a critical number of the function k as well, okay, but we'll notice, of course, right, the derivative at c in fact doesn't exist. All right, I was using my sort of bluish color here. Okay, So notice when we're talking about critical numbers, there is a relationship here to the derivative. We'll investigate this a little further in this section, and we'll use it in future sections as well. The derivative can be associated with critical numbers, and so far we can see that we can locate critical numbers if the derivative is 0 or if the derivative doesn't exist. Okay, right now we're recognizing that from the graphs. But if we were doing this with symbolic functions, if we did not have the graph, or if it was expensive to create the graph, right, we can use a symbolic form of these functions. If we can calculate the derivatives, we can then check to see when the derivative is equal to 0, when the derivatives don't exist, and that would give us some values that could be critical numbers for us to test further. What about if we take another look at, back up here on this parabola right here? Okay, so right, this graph to the right here, we had an absolute maximum. Right, we had an absolute minimum. And over here I said we had an absolute maximum, right? That absolute maximum was right here. Okay, the value at the vertex. What about an absolute minimum? Okay, that is, can we find a y value on this upside down parabola, a y value that is less than or equal to any other y value we otherwise could have attained? And by the shape of this graph, here we run into an issue, right? Run into a problem here. I was using red earlier for that minimum, right? Okay, it keeps going down, right? It goes down towards negative infinity. I mean, no matter where we choose to pick a point, if we say, well, this is the farthest down that I can see, whatever the y value is there, maybe that's the minimum. Is that the minimum? Well, it isn't, because as soon as we pick a location, right, as soon as we freeze it right there or plant a flag there, the function continues right past it. Well, then we have to choose a new location. Well, is that the minimum? No, because then it just continues even further, right? So this graph never actually attains the lowest possible value, right? Never actually attains its lowest possible value. So the graph over its entire domain, we say, has no absolute minimum, or that the absolute minimum does not exist. So no absolute minimum, okay, but it does have an absolute maximum. Okay, so the absolute maximum and minimum is to find the absolute maximum and minimum, we are really analyzing the entire domain of the function, right? We're finding the highest possible y value for the entire function, or the lowest possible y value for the entire function. Okay. Now, before we move on to the local ones, let's consider some other possible graphs. Okay, let's analyze them. Let's say we have a graph. Come on, get a straight line. There it is. Okay, let's say we have a graph that has a closed point one end, right, and then an open point at another end, something like that. Okay. All right, so now let's get some labels here. I'm going to call this A. We'll call this B. Okay, I'll call the in the output right here, right? The output right here. Let's call this y equals f of x. Let's go back to f. Right, y equals f of x. So this is f of a right here. Well, what about this value right here? Can we call this f of b? No, we can't, because f of b itself does not exist. In other words, the domain does not include b, right? Our domain of this function here, okay, is from the is closed at a and it goes up to b, but it does not include b. All right, so f of b does not exist. So that means the y value here, okay, all right, is not even attained by the graph, okay, or the function. All right, now on the other side, it's a little simpler. Okay, this seems to be it seems to be drawn in such a way such that the y value here is less than any other y value we might attain. Okay, so f of a is the minimum. In fact, not just minimum, right? It's the lowest y value throughout the entire domain. It is the absolute minimum. Okay, the absolute minimum of f. That is over its entire domain. This is the lowest y value that can be attained. Okay. Now what's happening over at b? Well, if we try to plug in b, we get nothing, right? We get no value. Does the function have a maximum? Well, we can't call that the maximum because it doesn't exist. Okay. But what if we tried to choose a value that was like really, really close to that? Right? What if we tried to pick a value that was really close to it? Okay, now I know I could choose a value like right there on the edge of this circle, right? But the idea here is that this is continuous right up to B, and it just doesn't reach B, okay? Okay, so if we choose a value that is just to the left, or try to choose a value that's just to the left, okay, of B, let's say I call this C, not because it's a critical number, but just because it's the next letter, right? C, well then there is going to be an output f of C. Is f of C a maximum? Okay, question is that a maximum value? And we can see, hopefully we can see that no, it is not. Why? Because we can then go between C and B, okay, by the density of real numbers. That is, that if we choose two real numbers, there is always going to be a real number we can choose in between those two. Always. Okay, there's always going to be another number we can find in between. And if we chose another number in between, like let's say D for this particular function, it would output an even higher y value. So is f of D the maximum? And the answer again is no, because now we can choose another value between D and B, call it, E or something like that, all right, or whatever. Right? We can keep repeating this process and we can keep getting higher and higher y values, but that never ends because this is open. Okay? So, what about an absolute maximum then for the function? This particular function f, okay, has no absolute maximum, or the absolute maximum of f does not exist. Okay? Every time we try to target the highest y value for this particular curve, there is always another y value that would be higher than that by the density of real numbers. Does that mean that if you have a discontinuity that it means that you're not going to have an absolute max or an absolute min? No, that wouldn't necessarily be the case either, right? We could have a function that, let's say does something like this, okay? All right, maybe something like that, okay? I'll have it approaching, maybe asymptotically approaching some horizontal asymptote in both directions or something like that, because that would be interesting, right? Okay, what about for this function? Okay, does it have an absolute max? Does it have an absolute min? Okay, does it matter that it has, an open point here? No, because we can still find, right, there's a lowest y value here, there's a highest y value here, right? So here's the maximum right here. That y value is the maximum, and here is the absolute minimum. Okay, so m is the absolute max in this case, and little m is the absolute min in this case. Now, if we were to remove this point right here, right, for instance, if I were to remove that point, then all of a sudden it would have no more absolute max anymore. The absolute max would not exist, because if it did have a highest point, that would have been the highest point. Right? So if we remove that point right there, then suddenly it would have no absolute maximum. What's another way we can take away an absolute maximum? Again, asymptotically. Right? If it goes off to infinity, we saw that above with the parabola here, facing downwards. Okay? So if we had a function here, okay, that, okay, all right, let's say we have a function that does something like this. Okay, maybe I have it approaching a horizontal asymptote right there, okay, but also maybe approaching a vertical asymptote right here. Okay, regardless of what happens then on the other side of this asymptote, if anything at all. Okay. How about I have a function, how about a rational type function that does something like this? Okay. Now in this case, no matter what point we choose, there's always going to be a point that is lower than that, and no matter what point we choose, there's always going to be a point that's higher than that. So this would be an example of a function that has no absolute max and has no absolute min. Okay, that deals with the absolute max and min, and we'll return to that later with a process to find these called the closed interval method. The closed interval method, which is where if we are given a function that is continuous on a closed interval, then the theorem, the extreme value theorem is a theorem that states that if you have a continuous function on a closed interval, you're guaranteed to reach an absolute max and an absolute min, and we'll take a closer look at that theorem later. But as a result of that extreme value theorem, and along with Fermat's theorem, which has to do with the critical numbers, okay, we'll be able to to first say that a continuous function on a closed interval must have an absolute max and absolute min, and furthermore, we'll have a technique that we can apply to locate exactly what that max and min are without using the graph. So if we just had to do this with a symbolic function. All right, and now I want to talk about the local max and min. All right, so a local maximum is a value of m. Okay, again, if it must be attained by the function. That is that in this case, again, we're going to call f of c is the value of that maximum. That means f of c must exist on the graph. Okay, and c must be in the domain. Okay, and furthermore, f of c must be the largest y value now within a local region. That is, f of c, which is equal to capital M as well, must be greater than or equal to any other f of x we could have attained for any x that is near c. And by near c, we mean we need to be able to create an open interval that goes to the left and the right of where x is equal to c. And that open interval can be very, very small. It doesn't have to be large, okay, in order for it to be local. But we have to be able to create an interval that looks to the left and the right of c. And where f of c is the greatest possible value of y that can be attained within that interval. Okay? The value f of c as a maximum can be attained more than once within that little interval, okay? But it only looks within a little localized region. Let's take a look at some local max and min possibilities. Local max and local min. All right. Let's say I have a graph function. It comes down like this. Maybe it goes up, down a little further, up, and then how about for something interesting, how about we go around a corner right there? All right, there's a corner. Remember that a corner is where the derivative from the left and the derivative from the right are not equal to each other, but they are both finite. So the derivative of, if we were to graph the derivative of this function, we would see a jump discontinuity. The other type of feature that looks more or less like that is a cusp. And when we have a cusp, okay, a cusp is formed when we are approaching a vertical tangent. And a vertical tangent would mean that the slopes of the tangent lines are approaching either infinity or negative infinity. Okay, and the graph of the derivative around a cusp is going to contain a vertical asymptote because the derivative would be approaching infinity or negative infinity. And around a corner, we have finite slopes, but those slopes are not equal to each other in the sense of the limit. Okay, so the derivative itself does not exist at that point right there. Okay, do we have local maxima and local minima, okay, on this function? And if so, where are they? Okay. In order to define a local maximum, okay, it must be the highest y value within a little neighborhood. That is an open interval that we could create around, okay, around the critical number c. Where on this graph might we have features like that? Right. Let's choose purple for max here. Okay, so in here, right, there's a point like here that looks like that is the highest point on this little hilltop here. So that is a local maximum, not an absolute maximum. Notice there are higher y values over here, so it's certainly not the highest y value we can attain anywhere. But we can construct a little interval, and we can make it smaller than that, okay? But we construct a little interval around whatever the input is. Okay, I'm going to call this input right here C1, okay? C1, okay, is that value right there. So the output right here, I'll call this function f of x. Okay, let's call this f of c1. Okay, then f of c1 would be a local maximum of the function, since f of c1 is greater than or equal to f of x, okay, for all x which are quote-unquote near C1. And by near C1, we mean in that interval. Okay? This interval right here. I'll call this interval, if I call this interval I1, okay, then if x is contained within the interval I1. So for any other value of x that we could choose within this interval, let's say I choose a value of x like right here, the associated y value for that x is not greater than f of c1. Again, the y value that we get could be the same as f of c1 and it would still be considered a local max, okay, but it can't exceed it within some localized neighborhood. Okay, if you're if the function is such that the neighborhood you're considering, okay, if we say, I wonder if this is a local max, if you construct a big neighborhood, a big enough neighborhood, you might eventually find a y value that is larger than it, but then the fix to that is construct a smaller neighborhood. It's the idea is if you can construct a neighborhood that is small enough, but it must be to the left and the right of the critical number, such that the output of the critical number is the greatest value that you can find within that region. Okay? C1, okay, is a critical number of f. That is, it's a value of interest to us that we're going to want to check to see if we find a maximum or a minimum. Okay, so we found a local maximum, okay, and the associated critical number was C1. Okay. The definition of a critical number, actually, let's look ahead at that because we've already been talking about it. A critical number is a value in the domain of a function, so a number c, okay, so it's a value of x if it's f of x, or t if it's f of t, or something like that, right? Critical numbers are values within the domain such that we know something interesting about their derivative. That is, either the derivative at that number is 0, or the derivative at that number does not exist. Because it turns out, if we have a function such that at the derivative at some value is 0 or the derivative does not exist, then there is the potential that the function reaches either a maximum or a minimum at that value. Okay, as we can see here geometrically, if the derivative is equal to 0, well then we have the slope of the tangent line is going to be 0, as would be the case here, right, in this particular example. Right, the slope of the tangent line, notice, okay, is equal to 0 there. So we can write notice f prime of c1 is equal to 0. Hence it is a critical number of f. Okay, so that's the tangent line right there. All right, the other possibility for critical numbers is that f prime of c does not exist. Where might the derivative not exist? One possible location where a derivative would not exist is right at a place where you would find a discontinuity in the derivative, right? Like here, like at this corner. Okay? So if there is a point here, and that point has an output that is the greatest output within a localized area, right? It's not the greatest y value for the whole function, right? In fact, this y value is larger than that y value. Okay? But the y value we get here is larger than any other y value we would get, right, within a neighborhood that we can stretch to the left and the right of the value of the input there. Let's call the value of the input C2. Okay, and then let's call this interval here, I'll call this interval I2. Okay, so I2 is an interval around C2. The output, okay, the output right there, let's call this is the point with coordinates what? C2, f of C2. Okay, so the output f of C2 is a local maximum. Okay, f of C2 is another local maximum. Now, f of C1 is a different value than f of C2, so we have more than one y value that is considered a maximum here now. Each one is the maximum within its own neighborhood, or locally. Okay? So again, by the same definition, right? Since f of C2 is greater or equal to f of x, okay, for all Okay, now there's a symbol that we have in math that means for all, and it's like an upside down A, right, with a larger cross there. That means for all. So for all x near C2, I can say for all x contained within or an element of the interval that I've called I2. Okay, so for any other value of x that we could choose within this little interval here, the associated y value will not be higher than the y value we get here at this point. What do we notice about the derivative at that point? Okay. Because this is a corner, right? The derivative does not exist there. So f prime of C2 does not exist. Right? And C2 is a critical number of the function f. Okay? So again, a critical number is defined as a value within the domain such that either the derivative is equal to 0 there, or the derivative does not exist there. Okay. Does that guarantee that they have to be maxima or minima? No, it does not. Okay. Before we take a look at minimums here, okay, or minima, okay, consider if we had a function. I'll give one to you symbolically. Consider this case, where we have a function that looks like this. Okay, like the function f of x is equal to x cubed, I'm thinking of. Okay, so you notice that if we take the derivative of this function, we get 3x squared, and if we set that equal to 0, then we get x equals 0. In other words, f prime of 0 equals 0, right? We found a value in the domain for this function. We found a value within its domain such that derivative would equal 0. Well, that means that 0 is a critical number. Okay? The input 0, this is a critical number. Okay? It's a critical number, okay, of the function f. Does that mean that that when we plug 0 in, we get a maximum or a minimum? And the answer, look at the graph and see. Is that point a maximum or a minimum? It is not. It's not an absolute one because, well, this graph, notice, has no absolute minimum. It keeps going down. Right? It's not an absolute maximum. Notice that the graph keeps going up. It's not an absolute maximum either. Okay? Is it a local one? If this was a local maximum, then we should be able to create an interval around it such that for any other value of x we choose within that interval, if this was a maximum, for any other value we choose within this interval, we should not be able to find a y value higher than this. But notice to the right, no matter what x value we choose to the right of this, we will attain a y value that is greater than 0. Okay, so it is not a local maximum. Okay, there is no local max on this graph. And similar argument for, is it a local minimum? If this was a local minimum, then we should be able to create an interval here, even a really small interval. If it was a local minimum, we should be able to create an interval whereby there is no lower y value anywhere within that interval. But to the left of this point, no matter how small we make this interval, to the left of this point, there is always going to be a y value we could attain that is less than this. Okay? So this function has no local minimum. Okay, so it's possible to have, so a couple points here, right? It's possible to have a function that has no maxima or minima of any type. That's possible. And it's even possible for the function to have a critical number, but that critical number doesn't guarantee that you're going to have a maximum or a minimum. Okay? All right. But, okay, again, the point of the critical numbers is if we're dealing with a symbolic function, as I'm demonstrating here, if you're just given a function and you don't have the graph, suppose you're just given the function symbolically. If you wanted to find the potential maxima and minima of that function, you want to consider first what is the domain of that function, so that you're checking throughout the entire domain. And then you want to check to see what are the critical numbers for this function. How do you find critical numbers? Take the derivative, and then you set the derivative equal to 0 and find all values of x, or the input variable, that make the function equal to the derivative function equal to 0. And B, determine, are there any values of the derivative, okay, any values of the input such that the derivative does not exist? That is, check the domain of the derivative. Okay, so so you want to check the domain of the derivative. Other than checking where the derivative is equal to 0, you also want to check what is the domain of the derivative. Now, in this case, the domain of the derivative is all real numbers, so there's nowhere to check to see if it doesn't exist. The derivative does exist everywhere for this function, f of x equals x cubed. But the derivative does equal 0, so it gives us a value that we should check to see if it's a maximum or minimum. It does not tell us that we are for sure going to find one, though. Okay, back to our graph up here. Okay, and now that we've dealt with local maxima, of which there were 2 of them, how about local minima? All right, so red for local minima. Okay, all right, the lowest possible point within a little localized neighborhood. I found one right here. Okay, so the input there, that's going to be a critical number. Okay, I'll call that one C3. And for any interval that we construct that goes to the left and the right, okay, we can still evaluate the function, but the valuation that we get, the y value, is never going to be less than the y value is at C3 as long as we are within this little neighborhood here. All right, so this is the point C3, f of C3. Okay, so we could declare that f of C3 is a local or a relative, is the other word you can use for it, local or a relative minimum. Okay? And that is since, symbolically, stating what we can see here graphically, f of C3 is less than or equal to f of x for all x in the little interval that we created around C3. Let's call this interval I3. All right? Okay, anywhere else? Oh, and by the way, what about the derivative there? All right. Since we found a local minimum, what do we notice about the derivative? Well, this happens to be one of the locations where the derivative would equal 0, right? It's nice and smooth there, and yeah, the derivative ends up equaling 0 there. Okay, so f prime of C3 is equal to 0. Okay, C3 is a critical number. Okay, C3 is a critical number. All right, any other minimums we can find? We got one more right here, a local one that is. All right, let's call this C4. So we can create a little interval around C4 such that any other value of x we choose within this interval would output a value of y that is not less than f of C4. Okay, so this is the point with coordinates C4, f of C4. Okay, we have a little interval here. Let's say I call this interval I4. Right. It's the same story again. And what about the and what about the derivative there? Nice and smooth there, so the derivative would equal 0 again, right? So it's the same story again. F of C4 is a local min. You know the reason why, because f of C4 would be less than or equal to f of x for any other x, okay, contained within I4. Less than or equal to f of x for all x contained within I4. Okay, C4 is a critical number, right? C4 is a critical number, and we see that f prime of C4 is equal to 0. F prime of C4 is equal to 0. We can see that from the graph. All right, now how about absolute max and absolute min? Okay, if all that we had to choose from were these 4 points right here, notice then this f of C1 would be the maximum of the maxima, right? The f of C1 is the highest y value of all of these points within here, but the graph continues out in this direction. We have to consider now, with absolute or global max and min, we have to consider the whole domain. And when we look at the whole domain here, right, we say, well, we can find y values that are higher over here, and this keeps going up. So in fact, this has no absolute max. Now, if it reached an endpoint, by the way, out here. We should start talking about endpoints right now, all right? I've been dealing with this function this whole time. Now I'm going to go and change it, right? That's okay. Let's say that this reaches an endpoint right there, okay? What's going on at that endpoint? Well, what's the y value right there? Let's find out what the y value is. Let's say that this is occurring at, let's say this is the point C5, f of C5 now. Okay. Let's choose a different color for the absolute now, right? How about green, right? A nice solid green. See if that'll work. Okay. This is all about finding local max and min, but now I'm going to throw in the absolute max and min, right? Okay. Well, it looks like now that what f of C5 is the absolute maximum of the function f, that it is the highest y value we attain over the whole domain now. And the domain is from C5 all the way out to infinity, by the way, I might mention, right? The domain of f is now closed at C5 and it goes all the way out to infinity. That's the entire domain. And over that entire domain, the y value we get here at C5 is the largest y value of any. Now, by the way, what about the derivative there? Right? The derivative in general is not defined at that point because we cannot look to the left. What about, is it a local max? It cannot be considered a local max. Okay? It cannot be a local max. Why? F of C5, okay, is not a local maximum. Okay? Why? Because we cannot choose x within an interval where C5 is contained entirely within that interval. We cannot choose x, okay, in an open interval around C5. So it does not count as a local maximum. Right? We can choose values of x to the right of C5, but we cannot choose values to the left. If we try to choose value of x to the left, the function is undefined there. Okay? So we do not count this as a local maximum, and we want to maintain that distinction here for now. Okay, so that we can consider it. With respect to the limit, we need to be able to approach from the left and the right if we're considering where we have a local maximum and a local minimum. But on an absolute one, right, an absolute maximum can be reached at an endpoint of a curve. But a local maximum or a local minimum cannot be reached at an endpoint because of the fact, by the definition, for a local maximum and a local minimum, you must be able to construct an interval to the left and the right of the input value. And it's never possible to construct an interval to analyze when you're looking at an endpoint, right? An open interval, that is, when you're looking at an endpoint, okay? So we're not going to classify an endpoint as local max or min, but we can classify an endpoint as an absolute maximum or an absolute minimum. Okay? What about for an absolute minimum for this graph? We take a look, what is the lowest y value that we will attain? Well, it looks like the function is trying to continue to go down. And that is my intention here. Okay? I was intending to draw it that way, that the function will continue to go downward. Okay? Continues to go downward below what this y value was. Now, if it didn't go downward, right, even if it turned around and let's say it approached asymptotically, some horizontal asymptote over here, well, then f of C4 would become not only a local minimum, but then f of C4 would also be an absolute minimum because it would be the smallest y value for the whole function. And it is possible for a y value to be both a local and an absolute maximum, or a local absolute and a local and absolute maximum, right? All right, but this function as constructed has no absolute minimum. Okay. We'll go orange. No absolute minimum. All right, so different types of features of this graph, right? A lot going on here. We got local, we got absolute stuff going on, we got possibility of not having absolute stuff. We learned about critical numbers and how to recognize them with respect to a graph. Okay, let's take a look now at a symbolic function and start trying to answer the questions about, well, where would you find the local and absolute maxima and minima of a symbolic function? And the first one I'll give is actually going to be, I'll do a piecewise function here. Okay. So example, sketch the graph of the function f of x and find all extrema. That is all local and absolute maxima and minima. Yeah, let's find all of those after we sketch the curve. I think I could do this over, fit this over here, and I can put the graph on the left. So f of x is equal to x squared. Let's say from -2, close there, x is, how about less than 1? Let's have a linear branch, 5 minus 2x. 1 is less than or equal to x is less than 3. All right. Let's create a sketch of f of x. What is the domain? I'd like to find the domain of f of x. The domain of f of x is, well, x can be equal to -2, and that's the smallest x value possible, from -2 to 1, but this does not include 1, but then 1 is included on this second piece, and then up to 3, but not including 3. So the domain is closed at -2, open at 3. All right, so let's see, -1, -2. I'll expand it a little bigger than that. Okay. There. -1, -2, and then let's see, 1, 2, 3. All right, so at -2, right, f of -2 is equal to -2 squared. That's 4, so the point -2, 4. -2, 4. Okay, it's right there. Is it open or closed? -2 is included in the domain, so this is going to be a closed point. The curve is y equals x squared. We know that looks like a parabola opening upward. It has a vertex at 0, 0, and x equals 0 is included. It's going to be that until x is equal to 1. Okay, so we have the limit as x approaches 1 from the left of f of x is what? Well, x is less than 1, okay, and so we're on this branch, and so as we get closer and closer to 1 by continuity, this is going to be 1 squared, okay, and that equals 1. But it is going to be open there because x does not actually equal 1 on this branch, right? So at 1, 1, we have an open point. And between these 2 points, we connect them along the parabola y equals x squared. Right, you should also have a point here this to try to guide my curve I'm trying to sketch here. Okay, so right, so it's part of y equals x squared. All right, there you go, but it's open there at the point 1, 1. All right, now the other piece starts when x is equal to 1. Now when x is equal to 1, that is, what is f of 1, we get 5 minus 2 times 1, that is equal to 3. So we're at the point 1, 3. That is going to be closed, a closed point. So a closed point here at 1, 3. It's a line. It has a slope of -2. It goes out to x being closer and closer to 3. So we can take like the limit as x approaches 3 from the left of f of x, and that would be, by continuity, we can say this is 5 minus 2 times 3, and that equals -1. Okay, so then we'll go down to here, that's -1, out to 3, down to -1. Oh, sorry about putting these numbers so far down here. So this is 2, right, this is 3, here's 1. All right, so 3, -1 is right here. Is that open or closed? 3 is not included in the domain, so this is going to be an open point right here. Okay, and connect these two in a line segment. I'm going to fix that a bit because I got the x-intercept should be around 2.5, right? Right, if you set this equal to 0, right, you get 5 halves, which is 2.5. So halfway between 2 and 3, it should be crossing. Okay, there we go. Here's our graph, y equals f of x. Find all extrema. Let's start with, how about we take a look at the whole graph in entirety, over the whole domain, and let's look for the absolute max, absolute min. Okay? So over the entire domain, okay, what is the highest y value that we attain if there is a y value that is actually attained on the curve, okay, that is higher than any other y value? And I find it right here, and it is at an end point, okay? So the y value there. Okay. Locate these values with that, with the red, okay? So this point right here, okay, as the coordinates -2, 4, okay? So we have that 4, looks like 4 is an, let me write the function, f of -2 is equal to 4 is an absolute maximum, right? An absolute maximum of f. Okay. What about over the entire domain? What about an absolute minimum? Well, all the values, all the points that we could choose over here, it looks like there's a minimum here, but it's not it is not the minimum of the entire function, right? Because there's lower y values over here, but we're approaching an open point here. So we'll notice, because this is open, right, this function has no absolute minimum. In other words, the absolute minimum does not exist. Is another way we can say that. The absolute minimum does not exist. Okay? If this point were filled in, right, if this were a closed point, then the y value there, which is -1, -1 would be the absolute minimum if that were a closed point. All right, so we found that, so we've already analyzed absolute max and absolute min. Okay? Now how about locally, local behavior? So what does the local behavior look like? We need to be able to construct little intervals in order to find local min, local max, for instance. Okay, now the definition is, right, for a local min, it needs to be the lowest y value within an open interval. Okay? So, for instance, here, right, this point right here, right, which we know from the function is it's the minimum of this. It's 0, 0. Okay, is that point right there. All right, so we have f of 0, which is equal to 0. Okay, that is a local minimum. Okay? A local minimum of the function. All right, any other local minima? Okay, for this particular one, there's no other point that we can choose that is the lowest point within an open interval. How about local maxima? Well, we don't have any points whereby the derivative would equal 0. That is, at a nice smooth hilltop, for instance, something like that. Okay, we don't have any of those. We do have this point here. What's going on with this point right here? Okay, that's the point with coordinates 1, 3. Is that a local maximum? Does it satisfy the definition of local maximum? That is, if we construct an open interval around 1, around x equals 1, okay, are we able to find y values to the, are we able to find points, first of all, are we still in the domain, right? Can we choose values of x to the left and values of x to the right? Are we still within the domain of the function? Yes, we are, because the domain is from -2 to 3, entirely between -2 and 3. So we can choose x's to the left and the right. We don't have to even have continuity then, necessarily. The definition doesn't state we need continuity in order to define a maximum or a minimum. Right? It doesn't say anything about continuity. We just have to be able to choose y values close to it. So when we look to the left, okay, and we look to the right, what we get are y values, okay, y values from these points, for example, that are all, in this case, less than the y value here. So we can construct an open interval, right, around x equals 1. And the output at x equals 1 is the highest y value we would get within any such open interval that we do, as long as it's a small enough open interval. So it satisfies the definition, right? F of 1, which is equal to 3, is a local maximum for the function. Okay? So the actual value of the local maximum is 3. The value of the minimum is 0. Okay? These are the values of the maxima and the minima. 4 is the value of the absolute maximum. And the absolute minimum does not exist. Okay. Here's a quick one. Sketch. F of x is equal to 3. The constant function. And find all extrema. Okay. 1, 2, 3. All right, horizontal line. Here we go. There's our function, y equals f of x. F of x is equal to 3. Y-axis, x-axis, 1, 2, 3. Okay. Find all extrema. Now, the domain, all real numbers, right? Negative infinity to positive infinity. Okay. Is there a point on here such that the y value for that point, and here's the key, for absolute, as well as it will be true for local as well, for the y value for that point is greater than or equal to the y value you could find at any other point throughout the entire domain. And for locally, can we construct an open interval around such a point? Okay, such that the y value at that point is greater than or equal to the y value at any other point within that open interval. And it's the same idea for minimums as well. Minima. So let's take this point right here. So what's that point right there? Well, let's say the input is c. It's just some value within the domain here. Okay, I'll call this one c1. Okay, well, this is the point with coordinates c1, comma 3. Notice that 3, okay, here we go, f of c1, which is equal to 3, does satisfy that it is greater than or equal to f of x for all x in the entire domain, because we're allowing it to be equal to as well for any other point. Since this is true then throughout the entire domain, and we say, well, therefore, 3 is the absolute maximum of the function f, right? It satisfies the definition. It does. We could have chosen, a point over here, c2. Okay, we get c2, 3. And again, f of c2 is also equal to 3. And we can do this again and again and again, right? The point is, it's the output that is actually the maximum. Okay. So absolute maximum. Is it an absolute minimum? Well, 3 is also less than or equal to f of x for all x contained within the domain, right? Because we're allowing it to be equal to. So, we would also conclude that 3 is the absolute minimum. Oh, there you go. The absolute minimum for the function f as well. It's both the maximum and the minimum for this constant function. What about locally? Okay, local behavior. Can we construct an open interval around C1? That is, can we look to the left and the right and still be within the domain? Yes. What do we know about the outputs for any other value of x that we choose within that open interval? Right? Are those outputs ever going to be greater than 3? No. Are we allowing it to be equal to 3? Yes. With local, you're still allowed to be equal to, whether it's maximum or whether it's minimum. Okay. So that means that f of c1 is a local maximum and a local minimum. Okay. We also have then that f of c1, okay, is a local a local minimum. Because f of C1, well, it is a local minimum, right? Okay, I was starting with maximum. Is a local maximum of f, right? Since f of C1, okay, is greater than or equal to f of x for all x that are near C1, that is within an open interval. Right? So near means in an open interval, right, containing C1. In other words, C1 is an element of some interval that contains C1. All right, I didn't name it right now. That's fine. In an open interval containing C1. So f of C1 is a local maximum of f. But so is f of C2. Okay? F of C2 is a local max, etc., etc. This would be true for any, right, for any value we choose within the domain. If I choose value here C3, another local max. If C4 is right here, another local max. C5, another local max. So there's an infinite amount of local maxima. Okay? So in fact, okay, or let's say it this way. In fact, there are an infinite amount, or I should be saying this more explicitly, right? An uncountable number of local maxima, okay, on F. And, I might add, also an uncountable number of local minima. Right? Because we could say that, you know, f of C1, okay, is a local min, f of C2 is a local min, etc. Right? Because for any one of those, we can always say that f of C1, right, is less than or equal to f of x, right, for all x near C1 or Ci in general, right, for any C. An uncountable number of local maxima, right, an uncountable number of local minima. Next on the list, let's take a look at the extreme value theorem. The extreme value theorem. If f is continuous on the closed interval a to b, then f attains an absolute maximum f of c and absolute minimum f of d at some c and d in the closed interval a to b. This is an example of what's called an existence theorem. An existence theorem in mathematics is a theorem which guarantees the existence of something. It doesn't tell you where it is necessarily. It doesn't locate it precisely, but it tells you that it exists. And then if you're interested in finding out where it is, you can go further and see if you can find, use of other theorems in order to actually locate where it is. And we will do that. But the extreme value theorem tells us when we can be guaranteed that that absolute extrema exist. Okay, and this does not mean that you have to have continuity and a closed interval to have a maximum and a minimum. That's not what it's saying, but it's saying if the function is continuous and on a closed interval, then it must have an absolute max and it must have an absolute min. Okay. Let's take a look at some examples for the extreme value theorem. The extreme value theorem. Okay. If f continuous on a closed interval AB, so why this is important. It has to be a closed interval. It has to be continuous. Okay. Then f must have an absolute max and an absolute min somewhere within the closed interval. Okay. Let's take a look at some situations. Let's build some functions here. Start with some functions that are continuous on a closed interval AB. Let's say that I have A here and B here. Okay, So if the domain of our function is the closed interval from a to b, and if we're forcing it to be continuous, well, if it's continuous on a closed interval, recall that that means that it has to exist at the endpoints, that it is continuous from the right when we approach the point AF of A, and it is continuous from the left as we approach the point BF of B. Now, so one possibility is how I'll do this. I'll put this one up here. Okay? Let's say that here's our 2 points, and we must have continuity here, so let's sketch a function that connects these 2 points. Okay? Well, here's one possibility. What if it's a linear function? Right? What if it was just a linear function like that? That's continuous. It's on a closed interval. Can we see that it must have an absolute max and an absolute min? Okay, in fact, what is the absolute max? What is the absolute min? In this case here, we have that f of b is the absolute max, right? The y value there is greater than any other y value you could attain. Remember that f of b is not a local max because we cannot construct an open interval, but it is an absolute or a global max. And f of a, the way I've constructed this, f of a is certainly an absolute minimum. Right? Okay. So that's true. Now let's try another function. Let's choose with the same 2 points here. So I'll go in with a different color here. All right, let's draw a different function connecting these two. What if the function instead, it has to be continuous now on this closed interval. What if it connected from this point continuously to this point like this? Okay, there you go. So it has to include the endpoints as well. Does it have an absolute max? Does it have an absolute min for this function here? So again, let's call this one f of x, another f of x, okay? Now for that function, the one in blue, okay, let's start with the minimum, right? The minimum happens to be right there the way I've constructed it. So again, f of a would be an absolute minimum for this function. Now, can we see that it must have an absolute maximum? And the next question would be, where is it? But just from looking at the picture, does it have an absolute maximum? Right? We can see that it does, and an absolute maximum would be up here. There is a point up here, kind of a vertex up there, right? That vertex holds the maximum y value for the entire domain of this function over the domain from a to b, the closed interval. So where is that point? Well, the theorem says that there is going to be, within the interval a to b, there must exist a value of c and a value of d contained within the closed interval, okay, such that we could say that f of c is the absolute max, but f of d is the absolute minimum, for example, or we could exchange those. We're saying that there's 2 values within a closed interval here. Well, in this case here, right, the value of d, if it was f of d is the absolute minimum, well then the value of d that we're choosing here, okay, right, the value of d is equal to a. I'll write that over here, okay? So d is equal to a, the value of d that I'm talking about right there. There is some value that is within this domain such that it outputs the minimum, okay? And we're saying that there is some value somewhere within this closed interval that would output the absolute maximum, and so that would be the value that outputs this quantity right here. So there is some value c that is contained within this closed interval such that the output of that value, okay, is going to be, right, the absolute maximum, in this case f of c, right? So we have that f of c is the absolute max. Okay, so we've sketched 2 functions, okay, over a closed interval, 2 continuous functions over a closed interval that did have an absolute max and an absolute min. Okay? Now let's just try some more examples here. What if a and b, okay, I mean, it would be the same story if I put, if f of a was up here and f of b was down there. It's the same story. We can draw a linear one, absolute max here, absolute min there, right? Or we could draw some kind of a parabola. We're going to have a maximum at some central, or some value within here, and a minimum at the edge. Or if the parabola were facing the other direction like this, then this would be the absolute max right here at the end point, but the absolute min would be contained somewhere within the open interval instead. Okay? Starting to develop a strategy here, defining these things for what's going to be called the closed interval method. if we have a continuous function on a closed interval, we are guaranteed that there is an absolute max and absolute min. Now, where might they be located? The absolute max and the absolute min might be at an endpoint, right? It could be that they're both at endpoints. It could be that one of them is at an endpoint and the other one is not. Okay? It also could be that one or the other, or both, are located not at endpoints at all, but somewhere within the interior of the interval. And if it's inside the interval, if it's inside a closed interval, then guess what? We can construct an open interval containing it, because we would be entirely within the domain. Anytime there must be a maximum or a minimum contained within our interval, okay, then we can target it by use of the derivative. Do we see the strategy developing here? If we have a continuous function on a closed interval, then there must be an absolute max and absolute min. How do we find it? Check the endpoints. The endpoints might be the maxima and minima. Where else do you check? In the interior. But of all the values you can choose within the interior, of which there's an infinite amount of them, which one should you target? The answer, where the critical numbers are. Because a critical number will tell you where you might have a maximum or a minimum. What makes a number a critical number? If the derivative is equal to 0, or if the derivative does not exist. Okay, let's continue with this down here. So again, say, we had maybe 2 points that are offset like this, okay, or like we had up there, okay. What if we had a function that maybe did something like this? It went down, or it went up and then down and then up, and then maybe even it went, here you go, even more fun, right? It goes up and then down, and then let's say it went like that around a corner, back up, and then something like that. Right, we're looking right now for absolute maximum and maxima and minima, right? An absolute maximum and absolute minimum, right? Not just the local ones. We're really focused now on the absolute ones for now. Okay. Is this function continuous? Yes. What's the domain? Is it closed? Yes. Okay, right? Is f continuous on that closed interval? Yes. Okay. Therefore, by EVT, okay, right, therefore, by the extreme value theorem, okay, f must have both an absolute max and an absolute min. Let's see where they are. Okay. Let's see, red on this one, or sort of an orange right there, right? The absolute max would be located at this point right here, right? So absolute max, if the input for it is C, okay, that is we can notice we can also construct an open. Well, we'll get back to that, right? We can construct an open interval around this because we are entirely contained within this closed interval. We're not at the edge. Okay, we already know it's possible to have a max or a min at an edge, an absolute max or min, and we always must check the endpoints if we're searching for absolute maxima and minima. Okay, but we also always check the interior as well. So this is the point with coordinates C, f of C. And we would say f of C is an absolute max. And I'll also mention that it is also a local max. Because it is within the interior, we can construct an open interval. But f of C is the absolute maximum of this particular function. Anything curious about the derivative there? We are in an interior, right? An interior value. The derivative, notice, because it is smooth here, the derivative must equal 0. So let's make that note. Note, f prime of C happens to equal 0. C is a critical number of the function f. The extreme value theorem guarantees an absolute min. Where's the absolute min? In this case, it looks like it's right there. At that point, that is a corner. I tried to show that point is a corner right there. Okay? And the input is, let's say, D. Oh, sorry. I'm going to use a different color. I'll go purple. D. Okay? That point right there, which is meant to be a corner, okay, I have that f of D is the absolute minimum of the function f. Notice, it's also a local minimum, okay? And I'm trying to make that a corner right there so that I can add into this note, again, D is a critical number. It's a critical number because it's a value in the domain such that there might have been a maximum or a minimum there, okay? And what do we do to test a critical number? Okay, well, to see if we have a critical number, I should say, to see if we have a critical number, we check the derivative. What do we note about f prime of d? If that's a corner right there, then f prime of d does not exist. Okay? So the point d f of d, df of d is meant to be a corner here, so that's why I'm saying the derivative does not exist. Okay. So we can see graphically, right, this is the strategy that we're developing. Suppose we have a function symbolically. We do not have the graph of it, but we just have the symbolic function. But if it's a function that we can test for continuity, we know how to see if a function is continuous. Right? We recall how to do that from previously in the course. How to tell if a function is continuous without the graph. If it's built up off of functions that were otherwise continuous, for instance, right? If a function is continuous, and if it is constructed over a closed interval, then we already know that there must be an absolute max and absolute min. The next thing is, how do we find it? Well, since it's on a closed interval, check the endpoints, first of all. What are the y values at the endpoints? Jot those down. Y value at A, the y value at B. Where else should we find y values? Right, we're not using the graph now, we're just using a symbolic function. We're just listing these y values. We should also check for the y values using the derivative. That is, look for the critical numbers. Find the derivative of the function, set it equal to 0. Solve the resulting equation. Okay, solve the resulting equation for all the values of x that would make the derivative equal to 0. Those are all critical numbers. Check the y values in the original function for each of those critical numbers and include those in your list that you're now constructing. So you now have the y values at the endpoints and the y values where the derivative would equal 0. Check where the derivative does not exist within the closed interval. That is, look at the domain of the derivative. Right? If there are breaks in the domain, discontinuities in the domain, okay, of the derivative, okay. In this case, notice that the derivative f prime of d, okay, would not exist, but d here was contained within the closed interval. In other words, d was within the domain of the original function. But d is not in the domain of the derivative. And because it's not in the domain of the derivative, it's a value we should check out of interest. Well, we need to check if f prime of d does not exist, then what we should do is check out what the y value was in the original function when we plug d in. Okay, so we want to collect these values. In this example, if we had the symbolic equation for it, we would be checking what is f of a, f of b, f of c, and f of d. We would have a list of 4 y values. We'd say, what is f of a? What is f of b? What is f of c? And what is f of d? And those are each going to give us numbers. Of this list of numbers, the highest of those numbers would be the absolute maximum of the function. And the lowest of those numbers would have to be the absolute minimum of the function by the closed interval method. Now, what if it wasn't on a closed interval? Right? What if we had continuity, but maybe did not have a closed interval? So we've seen that the extreme value theorem works as long as we have both continuity and closed interval. Okay, so now, what if f was continuous, okay, but not on a closed interval AB? What if the interval was not closed? Okay? Let's take a look at some examples like that. Here's an example. Suppose we had an A and a B. Okay, and by the way, if it's not closed, if we're talking about if the interval is something like A to B and then it's open like that, right, then we could really even be considering intervals that are like 0 to infinity. Okay, in general, not to say that B is equal to infinity, but the idea is if it's an open interval, we can extend this idea out to infinity. All right, that is a function that is on a domain that goes to either negative infinity or positive infinity. there's the potential that it will have no absolute maximum, or that it might have no absolute minimum as well. We can take a look at examples like that. So now let's say that this is a closed point, but let's say this is an open point. In other words, now we have this is the domain from A to B, but it's open at B. If we try to construct a function that is still continuous, right, still continuous here, right, but it doesn't exist at B, then what is the consequence? Notice there is no absolute maximum for this function. Now, does this kind of construction guarantee that there is not an absolute maximum? Now, there is an absolute minimum, right? We have in this case, okay, f of a is the absolute minimum. Okay, so you might still find it. But the theorem states the only way to guarantee that both of them will exist is if you have continuity on a closed interval. If either one of those, continuity or the closed interval, right, is not there, then you just don't have the guarantee. You might still find them, but you don't have it that it's guaranteed. Right, so for example, if we had this same situation, but if we had that parabola kind of a thing, like this, it's still open there, right? We still have the domain is closed at A, but open at B. But in that case, notice, well, we still would have, right, f of A is an absolute min, okay? But we would have like an f of C is the absolute max. So it's still possible to have both when you don't have, let's say, the closed interval, for instance. And we could show that it's also possible to have both even if you break continuity. It's just that you can't guarantee that you would have both. All right, so we showed what if it was open at one of the endpoints, and the same if it was open at the other endpoint at A, right? You know, then we could show that, right, that if it was open at A and open at B, then it's possible that it has neither. It's possible that it has both. Okay. Let's see. Right, if we have A, B, if we have it's open here, and then let's say it's also open there, okay, but if we even if we still have continuity, okay, it's possible, you know, to construct a function such that we have absolute max and absolute min, right? So that's possible, even if the domain is open, but it's just not guaranteed, right? Because of course, right, we could have a function that's open here and open there, right, and it could do something like that, okay, and in that case we have no absolute max, right, no absolute min. All right, so we need the closed interval is the point. We need the closed interval in order for the extreme value theorem to guarantee the absolute max and absolute min. What about continuity? What if f is not continuous on a closed interval? So now let's say we have the closed interval, but we don't have the continuity. What might functions look like in that case? Okay. We could have a function from A to B. Okay, maybe it's defined here and it's defined there. Okay. What about this situation? What if we had a vertical asymptote here? Is this possible? Right? What if we had a function that approached this asymptotically, and then it could go either up or down, either way. Let's say I have this one going up. But how can, you know, so this is not continuous, right? Not continuous. But how can I make sure to define this on a closed interval, A to B, that it has to exist at all values between A and B? Well, we could put a point that is not on the curve, like a point here. Okay, now its domain, okay, now the domain of this function is, in fact, a closed interval A to B. Okay, if it happens that we choose, I'll call it C. Let's say x is equal to C. Okay, then C is value between A and B, and the function is defined there. And it's defined to the left of C, it's defined to the right of C as well. Okay, so it is defined over the entire closed interval from A to B, but it is not continuous. And as a consequence, we can see, look, there is no absolute max, right? Because it just keeps going up. For this function, there is an absolute min. It turns out that f of a, though, is an absolute min. Okay? Right, so the point is that we don't have continuity. Here's one case that shows, okay, that we have, right, that we might lose either one or the other, absolute max or absolute min. Okay, so there is a type of discontinuity, right? The infinite type of discontinuity. What are the other types of discontinuities we could have? How about a jump right? A jump discontinuity we could have. A, B, closed interval, right? We want the domain to be the closed interval from A to B. So we have, let's say, a point here. Again, let's say a point, right? I keep doing it in that direction. But let's say I have this point up here, and maybe this point over here, or it could even be a constant, they could be the same value. Okay, it just exists there and exists there. But let's say that at some intermediate value C, let's say that there is a jump, right? Let's say that we approach from one direction, and let's say that it's open from the one direction. Okay, but maybe it's closed from the other direction, something like that. Okay, so here we have a jump discontinuity. Does this function have an absolute max? Does this function have an absolute min? This point right here, okay, let's call this D right here. Then this is the point with coordinates D, F of D. Well, then for this function here, F of D is the absolute maximum. Okay? Even though we have a discontinuity, right? A jump discontinuity here. What about an absolute minimum? Does the function have one? It could have had one, but it doesn't in this case. In this case, right, it's approaching an open point here, and that would have been the minimum, okay, if it were filled in, but it is not. Okay, so the function has no absolute minimum. Do that. Right, this is discontinuous, right? This is an infinite discontinuity. This one is a jump discontinuity. Is it possible to have a jump discontinuity and still have a closed interval and still have an absolute max and absolute min? Yes. Right, we have the absolute max taken care of. We could do a similar type of a thing. Right, we could have attained an absolute minimum and an absolute maximum even with a discontinuous function. All right, but again, we've already shown that if it is continuous on the closed interval, we know we would have both. Very good. What's the other type of discontinuity we discussed in this course? Infinite jump removable. Okay, let's construct a function that has a removable discontinuity then, okay, but is still defined on the closed interval A to B. Okay, so here's A f of A, and then over here, let's say I have B f of B, but let's put a removable discontinuity in there at C. Okay, something like this. Okay, I want to make it obvious, right, that this is, okay, something like that. It approaches like that, and then over this way, right? For removable discontinuity, it has to have a limit from the left and a limit from the right are equal to each other, but it doesn't necessarily exist at that point. But we need this to exist throughout the entire interval, right? We need the domain to be all values between A and B inclusive. So we would need to put some point where it is defined. So this is the point where the output is f of c. Right, now this function, absolute max, absolute min, does it have either of them? Well, this point right here, f of b, right, f of b is an absolute maximum. And does it have an absolute minimum? In this case, it does not, because if it did, it would be at that location right there. Okay, so this function has no absolute minimum. Okay, so if a function f is both continuous and on a closed interval, there must be an absolute max and an absolute min. Right? The next thing is, how do you find them? Well, if it's continuous on a closed interval, you can check the endpoints of the closed interval, find the y values at a and at b. That is, find f of a and f of b. You don't need the graph to do this. You can evaluate it symbolically. And after finding f of a and f of b, you also want to locate all the critical numbers within the interval, a to b. Those are found by finding the derivative of the function and setting it equal to 0, and finding out where the derivative does not exist. That is, checking where the domain of the derivative as well. List the critical numbers. Then, what do you want to do with the critical numbers? plug them back into the original function to find the associated y values. Critical numbers tell you where the y values of the function may have been maxima or minima. With your list you've now constructed of all the y values of interest, the highest of those y values must be the absolute maximum. The lowest of those y values must be the absolute minimum. That is the closed interval method. All right. The closed interval method. If the function's continuous on a closed interval, okay, it must have an absolute max and absolute min. How do you find them? Find the values of f at the critical numbers. That is, f prime of x equals 0. F prime of x does not exist. List those values of the critical numbers. Find the values of f at the endpoints. Okay? So you're going to find f of each of the critical numbers, f of a and f of b, to create a list of all potential y values. The largest of those y values is the absolute max. The smallest is the absolute min. Now we've shown graphically that it seems reasonable that all this is true. But one more theorem that really should be established to demonstrate that this has to be true about the critical numbers, therefore, is that if we're looking for local extrema, local maxima and minima, that they really are in fact found where either the derivative does not exist or where the derivative is equal to 0 and not at some other points. Okay, so we know already if the derivative doesn't exist, we should check those points. They might possibly be associated with maxima or minima. That's one thing. Well, what if the derivative does exist? Just because the derivative does exist, that doesn't necessarily mean we have to have it's equal to 0, does it? What if the derivative existed but it wasn't equal to 0? Okay. Well, Fermat's theorem states with conclusive results by an if-then statement, if the function has a local max or a local min, it would be the same story. If it has a local max and the derivative exists there, then it must be that the derivative is equal to 0. Well, let's take a look at the proof for Fermat's theorem. Proof. Okay. Start by assuming that f has a local max at x equals c. Recall that what that means is that therefore that f of c is greater or equal to f of x for all x that are near c. That is in an open interval, okay, near to c. So let's look at this graphically so I can help you to understand what we're doing here. So c, f of c. So suppose that the function has a local max there, and this is what it would look like then, right? The function output is greater than or equal to the output anywhere else, and it could be that it's the constant function as well, right? This is one where the derivative does exist there, okay? And f prime of c exists, okay? Well then, that means that, f prime of c, all right, is equal to the limit as h goes to 0, okay, of f of c plus h minus f of c over h, for instance, right? If the derivative does exist. Okay, well notice if we construct an open interval, and this can be as small as we want, okay, if we choose a value of x that is within this interval that is near c, okay, if x is near c, okay, then we can say that x is, I'm choosing x right now to be to the right of c, I can say that x is equal to c plus h, where h is some very small number that is greater than 0. Alternatively, we can also choose a value of x that is to the left of c, where then we could say x is equal to c plus h, where h is less than 0, and that also is possible. We'll take a look at that in just a moment, right? So you can see how the proof works. So then we take this statement right here, which is what tells us that we had the maximum there, and we've now chosen the value of x that is near to c. Okay? So we have that f of c is therefore greater than or equal to f of c plus h, for h is greater than 0. Okay? Now we can subtract f of c from both sides. So this is f of c plus h minus f of c. And now we can divide both sides by h, where h is not equal to 0, so we can do that. So we can divide both sides by h. 0 divided by a non-zero number is just 0. So now you have 0 is greater than or equal to this right here. Right? And what is that? The difference quotient. So let's take the limit of both sides as h goes to 0, right? The limit as h goes to 0 of 0 over h. Remember, now h is not 0 when we do this limit, right? So it's 0 divided by a non-zero number, and that's just 0. But on the right-hand side, we have the limit as h goes to 0 of f of c plus h minus f of c over h. And what is that? Since the derivative must exist for this function at c, this is the derivative. So f prime of c. Okay, so what have we found? 0 is greater than or equal to f prime of c. What's the conclusion of Fermat's theorem? That f prime of c is equal to 0. Not that f prime of c is less than or equal to 0. It should be that f prime of c is exactly equal to 0. Well, we've just found, by choosing a value of x that is to the right of c, we've found that 0 is greater than or equal to f prime of c. Now let's go in and let's choose a value of x to the left of c. So let's let x equal to c plus h, where h is less than 0, right? So that means we're choosing a value within this open interval, but it's to the left of c. Okay. So also then, again, using this statement right here, that it must be f of c is greater than or equal to f of x within that interval, then we have that f of c is greater than or equal to f of c plus h. Here's where h is less than 0 then. How does the proof work out the same way? Subtract f of c from both sides. 0 is greater than or equal to f of c plus h minus f of c. Now divide by h. But now we're dividing by a number that is less than 0. What happens in an inequality when we divide by a quantity that is less than 0? All right, we divide both sides now by a negative number again, by a negative number. So that means we have to flip the inequality symbol over like that. Now we take the limit of both sides. The limit as h goes to 0 of 0 over h is less than or equal to the limit as h goes to 0 f of c plus h minus f of c over h. Because the derivative exists, then this is f prime of c. And this is 0. So now we have that 0 is less than or equal to f prime of c. Well, let's combine our results then. 0 is greater than or equal to f prime of c, and 0 is less than or equal to f prime of c. Combining those results, all right, we get that f prime of c less than or equal to 0 and greater than or equal to 0. But how is that possible? It's only possible to be greater than or equal to 0 and less than or equal to 0 if f prime of c is specifically equal to 0. And so that concludes the proof, at least if this is a maximum. The proof for the minimum is quite similar. Where does it change? With a minimum, this statement would switch. It would be that f of c is less than or equal to f of x, but everything else is done the same. So now it's confirmed. The critical numbers, therefore, can only be found where the derivative does not exist or the derivative is equal to 0. All right, now we can take a look at finding the critical numbers for some different functioning. Critical numbers are the values x equals c such that either f prime of c is equal to 0 or f prime of c does not exist. Okay? And these are the inputs. Okay? We're not looking for absolute max and absolute min in this example. We're just trying to seek out what are the critical numbers in a symbolic example. Okay? All right, so we need the derivative. Okay, we also should consider the domain. By the way, I'm going to consider the domain of this function. The domain of this function here, right? So we're taking a cube root. We can take the cube root of any real number. Okay, so therefore x can be any real number as well. Because you can square a real number, you're going to get positive. 4 minus a positive is either going to be positive or negative or 0. Okay, so the radicand here is going to be from negative infinity to 4 inclusive, but we can take the cube root of any number from negative infinity to positive infinity, so the domain is all real numbers. Okay, now finding the derivative. In general, f prime of x, use the power rule. Okay, well, the power rule in the chain rule, right? So f of x can be rewritten as the quantity 4 minus x squared to the power of 1/3, right? F prime of x then is equal to 1/3 times the quantity 4 minus x squared, subtract 1 from 1/3, you get negative 2/3. Now apply the chain rule, so we're going to multiply this by the derivative of 4 minus x squared, that is negative 2x. Okay. If we want to simplify that, clean it up a little bit, what does it look like? Negative 2x over 3 times, I'll leave this at 4 minus x squared to the 2/3 power. There's our f prime of x. Find the critical numbers. Okay, so on one hand, we want to set this equal to 0. F prime of x is equal to 0. So 0 equals negative 2x over 3 times 4 minus x squared to the 2/3. Okay? As long as the denominator is not also equal to 0, this would have solutions when the numerator is equal to 0. Okay, so negative 2x is equal to 0 when x is equal to 0. So x is equal to 0 is a critical number. Just to make sure, if you is zero in the 0 in the domain of the original function, right? And it is, right? It's between negative and positive, so that's fine. Okay, if this didn't exist at 0, that would be okay. It would still be considered a critical number, right? And if we were looking for then maxima and minima, this would be one of the numbers we would want to plug into the original function to find the y value then, and that would potentially be a maximum or a minimum. Remember that we can only guarantee maximum or minima if we had a closed interval. This is an open interval. We still nonetheless would have a potential maximum or a potential minimum when checking that critical number. Okay? And we wouldn't know if it was a maximum or minimum until we completed our analysis. Now, what's the domain? Okay, f prime of x does not exist. The question is, where does it not exist? Okay, well, let's look at the domain of f prime. All right, the domain of f prime. It is, all right, it's a fractional expression. Right? There's no issue with the numerator. The numerator is polynomial. All real numbers are okay in the numerator. The denominator, though, the denominator is a cube root. Again, all real numbers are fine in a cube root. Okay, and there's a polynomial contained within it. That's fine. But the denominator itself cannot equal 0. So we want to take that denominator, 4 minus x squared to the 2/3, and say, but that is not allowed to equal 0. What does that mean about x? Okay. So solve this equation, if you will. Right? I've negated it right here, right? But you're solving an equation. I'll start by raising both sides to the 3/2 power, right? Raise this to the 3/2 power, right? Because raising raising this to the 3/2, those exponents would cancel each other out by rules of exponents. All right, that's just equal to 0. Well, not equal to 0. That's equal to 0, right? So where does 4 minus x squared equal 0? 4 minus x squared, okay, is not allowed to equal 0 then. Okay, that means 4 is not allowed to equal x squared. That means x is not allowed to equal plus or minus 2. Plus or minus the square root of 4, right? So we have two more critical numbers here. X equals 2, x equals negative 2. Okay, those are also critical numbers. Okay, so if we wanted to list all the critical numbers here, the critical numbers for f, okay, we have the set of values, let's see, from lowest to highest, negative 2, 0, and positive 2. Now we'll work on a graphical analysis of functions so that we'll be able to create graphs of functions like this, that go beyond the type of graphs that we normally would construct in a pre-calculus setting. Now that we have calculus, all right, we can get a better idea for the shape of the graph, but that's coming up in a couple of sections. Okay, but an actual sketch of this graph, at x equals 0, we have the derivative is equal to 0, right? So we know that there is a horizontal tangent line when x is equal to 0. Horizontal tangent line when x equals 0. Now what is f of 0? We can go back to the original function and find out, right? We say plug 0 into the function, we get f of 0 is the cube root of 4. So some positive quantity. So at the point 0, cube root of 4, we have a horizontal tangent line. All right, so we know that there's a point here with coordinates 0, cube root of 4, and the tangent line at that point, all right, is horizontal. Okay, and now what about at the breaks in the domain at x equals 2 and x equals negative 2? Well, we can find the coordinates of those points as well. If we wanted to find out what is f of 2, plug 2 into this, right? We get the cube root of 4 minus 4, but that's 0. Same story for f of negative 2. f of negative 2, this is going to output 0. So the y value of the function would be 0 at plus and minus 2. So there's a point at negative 2, 0, and there's a point at positive 2, 0 as well. Okay. Further analysis, as we'll do in the future, we'll be able to establish, we could do it here, if you start plugging in values that are near 0 to the left and the right, you'll find lesser values. You'll find that this is actually a maximum right here. It's going to turn out this is a maximum. Okay. And what about at these points right here? If you start evaluating around these, again, notice remember the derivative does not exist at these points. How can we have at these points the derivative doesn't exist? Right, we'll probably either have a corner, a cusp, or a vertical tangent. And in this case, we're actually going to have vertical tangents, okay, for this particular function. All right, or we could take the limit, okay, take the limit of the derivative in order to find the how the slopes of the tangent lines would appear. So you can take the limit of this derivative as x approaches plus and minus 2 from both the left and the right. Okay. So we're going to have vertical tangents. So we're actually going to have a function, I think it's going to kind of curve over like this, and then it's going to curve out like that. It's sort of bell-shaped. Okay, so we'll take a look at creating the graphs of these types of functions in a bit. Let's start out by listing the domain for this function. So the domain, we have the difference of a polynomial and a tangent function. So polynomials all real numbers, but what about the tangent function? Tangent of theta, all right, remember it's undefined, for theta equal to pi over 2 plus k pi, where k is any integer. All right, so that's where, right, k is equal to 0, plus minus 1, plus minus 2, etc., etc. So this includes values like theta is pi over 2, 3 pi over 2, 5 pi over 2, plus or minus, plus or minus, plus or minus, right, etc. So the domain of f is theta is not equal to pi over 2 plus k pi, where k is an element of the set of integers. There's our domain. Finding critical numbers. All right, we need f prime of theta. We're going to set the derivative equal to 0 and find out where the derivative does not exist. F prime of theta is, let's see, 4, right? Derivative of 4 theta with respect to theta is 4, minus the derivative of tangent is secant squared, so secant squared theta. Okay, let's set f prime of theta equal to 0. We're solving 0 equals 4 minus the secant squared of theta. So that's 4 is equal to secant squared theta. That would be where the secant of theta is equal to plus or minus 2. All right, so we might recall that's the same as 1 over cosine theta is equal to plus or minus 2. By the reciprocal identity, plus or minus 2. And that's where cosine of theta is equal to plus or minus 1/2. Okay, so the derivative is equal to 0. That is, we would have horizontal tangent lines on the function f of theta equals 4 theta minus tangent theta at all the points where the cosine of theta is equal to plus or minus 1/2. Okay, so we want to be able to solve these equations. Cosine of theta is equal to 1/2. Cosine of theta is equal to negative 1/2. Let's start with cosine of theta is equal to 1/2. Where do we find solutions to that equation? Meaning, in which quadrants, right? In which quadrants of the unit circle would we find solutions to that equation? Right, this is my unit circle right here. Cosine is positive. Where is cosine greater than 0? In quadrant 1, right? Okay, that's where the x-coordinate is greater than 0. So cosine of theta is positive in quadrant 1 and quadrant 4. Right? So quadrant 1 solutions, quadrant 4 solutions. We can find one of those solutions with the arc cosine. So we take the arc cosine of 1/2, we would get the solution that is in quadrant 1. Right? So this is the quadrant 1 solution right here. What is the arc cosine of 1/2? In other words, do we know what angle in radians the cosine of that angle is equal to 1/2? That would be at pi over 3. So this equals pi over 3. So pi over 3 is a solution to this equation here in quadrant 1. That's not the only solution for quadrant 1. We have to include all possible solutions. Let's call this one theta 1. It's the quadrant 1 solution. So our set of all theta 1s would be pi over 3 plus 2k pi, where k is any integer. All right, so that would include angles like pi over 3 plus 2 pi. So if we went through a full rotation and then back again, okay, we would have another solution to this equation. An infinite amount of solutions, therefore, in quadrant 1. What about quadrant 4? We need at least one solution in quadrant 4. One solution we could find by symmetry here. If this angle is pi over 3, then this angle here is also pi over 3, but in the opposite direction. So a quadrant 4 solution, okay, I'm going to call that one theta 2. Okay, theta 2 is equal to negative pi over 3. And then if we add 2k pi to that, we get all other quadrant 4 solutions. Okay, so here's our quadrant 4 solutions. So this would be the set of all the solutions to this equation. Cosine theta is equal to 1/2. Therefore, at all of these values of theta, an infinite amount of values here, the derivative would have equaled 0. We also have to find all the solutions to this equation here. Okay, same way. Right, same technique. We want the cosine of theta is equal to negative 1/2. Unit circle, where is the cosine negative? In quadrant 2 and quadrant 3. How do we find either of these solutions? Well, we could start with the arc cosine. The arc cosine of negative 1/2. The arc cosine is going to give us the quadrant 2 solution. The arc cosine is defined, is going to give us solutions in either quadrant 1 or quadrant 2. In this case, we're going to get a quadrant 2 solution out of this. Okay, we already know the reference angle was pi over 3, and in quadrant 2, that means that this angle or this arc length is pi over 3, therefore this length right here, okay, would be a solution in quadrant 2, and that's 2 pi over 3. So that's a quadrant 2 solution. Let's call this theta 3. We have theta 1, theta 2, let's call this theta 3. So the set of all possible theta 3 would be 2 pi over 3 plus 2k pi, where k is an element of the set of integers. And how do you find the quadrant 3 solution? Again, we're going to use the reference, right? A reference angle. I box this set of solutions here. The reference angle here is pi over 3. Okay? If that's pi over 3, then the angle, then this, or arc length, then this arc length, or this central angle of rotation, is pi plus pi over 3, which is 4 pi over 3. So our set of, let's call these theta 4s, okay, theta 4, okay, is equal to 4 pi over 3, and then we add 2k pi to that as well to get all the quadrant 3 solutions. So these are all in quadrant 3. So this particular trigonometric equation had solutions in all 4 quadrants, right? That happened to be characteristic of this particular equation, right? It had solutions in all 4 quadrants, and here they are. Now these solutions actually, in fact, overlap. For instance, if we take pi over 3 and add 1 pi to that, we would get 4 pi over 3. Okay, so in fact, we could even say that theta 1 is equal to pi over 3 plus k pi. K is any integer. Okay, then by adding only k pi, notice if k is equal to 1, we would get 4 pi over 3. That would give us this solution right here. All right, and theta 2, All right, notice also we have an overlap here. If we add k pi to negative pi over 3, right? Well, negative pi over 3 plus pi is 2 pi over 3. So these also overlap. So we can say theta 2 is equal to negative pi over 3 plus k pi. And that's another way that we can express these solutions. Okay, so yeah, f prime of any of these theta 1s is equal to 0. And f prime of any of the theta 2s, those are equal to 0. These are all critical numbers because they're all values where the derivative would equal 0. Okay. Are we done? No. We have to find all the critical numbers. That's where f prime of theta is equal to 0 and where f prime of theta does not exist. So we need to know where f prime of theta does not exist. In other words, check the domain of f prime of theta. F prime of theta is 4 minus secant squared of theta. Okay, well, 4 is constant. What about secant of theta? Right, the secant of theta is undefined. Okay, we have 4 minus secant squared of theta. Well, that's the same as 4 minus 1 over the cosine squared of theta. This is undefined. Okay, this is undefined. F prime of theta undefined if the cosine of theta is equal to 0. Where's the cosine of theta equal to 0? Let's go to that unit circle again. Cosine of theta is the x-coordinate when you're moving around the unit circle. The x-coordinate is 0 here and here. For instance, at pi over 2 and negative pi over 2, or 3 pi over 2. And then if you add multiples of 2 pi, you'll keep returning to those locations again and again as well. So, where f prime of theta doesn't exist, it is undefined if theta is equal to pi over 2 plus k pi. Right? For instance, pi over 2 plus pi would be 3 pi over 2. Okay? Pi over 2 plus k pi, where k is an element of the set of integers. And so the domain, okay, the domain of f prime, that's what I was finding here, right? The domain is that theta is not equal to pi over 2 plus k pi, for k is an element of all sets of integers. Are these critical numbers in this case? Okay, are they critical numbers in this case? They would be if they were in the domain, but they're not in the domain of the function. So if we tried to evaluate the original function at any of those values, we would get undefined anyway. Okay, so are these critical numbers? They are not critical numbers because they are not in the domain of f. Okay? Notice, f prime of theta does not exist if theta equals pi over 2 plus k pi, where k is an element of the set of integers. But these theta are also not in the domain of f, the original function f. Okay? Hence, theta equals the pi over 2 plus k pi, okay, do not qualify as critical numbers for this problem. All right? So a couple interesting things happening in this example. A few interesting things, right? It's a complicated problem because of the trigonometry involved, solving some trigonometric equations. Also having the consideration of where the derivative does not exist actually overlapped where the original function didn't even exist. If you can't plug the numbers into the original function, that is, if those numbers are not in the domain of the original function, then they're not considered critical numbers, because you're not going to be able to evaluate the function there anyway. The critical numbers are meant to give us a list of potential places where we could find maxima and minima. Not to guarantee that they exist there, but where we could find maxima and minima. And we can't plug these values in, so we don't include them. The critical numbers that we would want to check would be all of these here, and that's plenty, because this is an infinite amount. An infinite amount of numbers that we would want to check, okay, if we were asked to do that. Okay, so a lot of practice in trigonometry there. Okay. Let's try one example where we do the actual closed interval method on a function whereby we're not using the graph, but just using the symbolic form of the function. Okay. Find the absolute max and the absolute min on the closed interval a to b for the function f of x equals x over x squared minus x plus 1, and the interval will be the closed interval from 0 to 3. Okay. First question, is f continuous on the interval from 0 to 3? Well, the numerator is polynomial, the denominator is polynomial. Let's make sure the denominator is not equal to 0. Does x squared minus x plus 1 ever equal 0? Okay. How can we check? Try to factor, it doesn't seem to factor so well, but what about if we did the quadratic formula? Okay, or in fact if we just check the discriminant to see if this works. Okay, negative b plus or minus, right, the square root of, we know, right? So the opposite of the linear coefficient, so negative b would be 1 plus or minus the square root of b squared, right, negative 1 squared, minus 4 times a, which is 1, times c, which is 1, okay, over 2 times 1. Check the discriminant, the b squared minus 4ac, okay, which is the negative 1 squared minus 4 times 1 times 1, okay, and that's equal to 1 minus 4, which is negative 3. That's less than 0. Right, so that's the discriminant right there. If the discriminant is less than 0, then we have non-real solutions. Okay, this has only non-real solutions. Okay, so there are no values, there are no real values of x. There are no real values of x such that this denominator would equal 0. Hence, this function would in general have, in fact, a domain of all real numbers. Okay. So the answer is yes, f is continuous on 0 to 3. Okay, it's built up out of a combination of continuous functions, and there are no discontinuities that we can find. So it is continuous. Okay, so we now have a function, we are given a function f on a closed interval, and it is continuous. So we know, therefore, by the extreme value theorem, right, the existence of the absolute max and min. By the extreme value theorem, since f is continuous on a closed interval, then there must be an absolute max and an absolute min, okay, on f, or of f, okay, in this interval. In order to find them, we want to check the y values at the following locations. We want to check what is f of 0 equal to. That's the y value at this endpoint. And what is f of 3 equal to, the y value at that point. Okay? Check those, and f of c, what is the y value for at any critical number, okay? For any critical number c. So we need to find the critical numbers, and we need to evaluate these as well. Okay, should we real quickly evaluate these? F of x is x over x squared minus x plus 1. So f of 0 is 0 over 0 squared minus 0 plus 1. That's 0 over 1, which is equal to 0. That's a y value that is for us to consider as a possible max or min. F of 3 is equal to 3 over 3 squared minus 3 plus 1. All right, that's 3 over 9 plus 1 is 10, then minus 3 is 7. So we get 3/7. We're going to want to check that. If that's the largest value in the list, it's the maximum, absolute maximum. If that's the smallest value in the list, then that becomes the absolute minimum. But we need the other values in the list. Find critical numbers, okay, for any critical number c. So we need the derivative, f prime of x. Okay? right? F of x is x over x squared minus x plus 1, right? So the derivative, right? Here, I'll write it down for you over here. F of x is equal to x over x squared minus x plus 1. Okay, so let's use the quotient rule. The low is x squared minus x plus 1 times the derivative of the high, so 1. Derivative of x is 1. Minus, so low d high minus high, which is x, d low. The derivative of the denominator is 2x minus 1 over the bottom function squared, the low. Okay, here's our derivative. What do we want to do? We want to check to see where is f prime of x equal to 0 and where does f prime of x not exist. Okay? Well, I think I'm going to want to simplify this a bit, clean it up so that we can do that algebra that we need to do. The numerator, we got x squared minus x plus 1, and then we got a minus 2x squared plus x. And the denominator has x squared minus x plus 1 squared. All right, simplify. Let's see, x squared minus 2x squared is negative x squared. Negative x plus x. Those two will cancel each other out. And then we have a plus 1. In the denominator, we have x squared minus x plus 1 quantity squared. Here's our f prime of x. Okay, let's investigate that. Okay, we want to see where is that equal to 0, where does it not exist. Okay, as far as domain, okay, as far as the domain of f, the numerator is polynomial, the denominator is polynomial, and again the denominator, if we try to set it equal to 0, it's the same factor that we already tested. So the domain of f is all real numbers, negative infinity to positive infinity. So f prime of x exists on all real numbers, but we're only interested really in the closed interval. It exists throughout the entire interval. No critical numbers are found by this not existing. If we have any critical numbers, they would be found wherever this is equal to 0. So let's set it equal to 0 now. 0 equals negative x squared plus 1 over x squared minus x plus 1 quantity squared. Okay. We can multiply both sides by the denominator, which is never going to equal 0. So now we're set solving 0 equals negative x squared plus 1. Solve that for x. X squared is equal to 1, so x is equal to plus or minus 1. We found values of x that would make the derivative equal to 0. Are these the critical numbers? X equals 1, x equals negative 1. We're supposed to be looking in this interval, the closed interval 0 to 3, and that's all the only place we're interested. But x equals negative 1 is not in that interval. Okay? It's not in the interval 0 to 3, so we're not interested in it. If we were looking at an interval that was, let's say, negative 3 to 3, well, then we would be interested in this one. Okay? But we're only, in fact, interested in this one, x equals 1. That's our critical number right there. And that's the only critical number we found, right? We had to see where the derivative is equal to 0 and where the derivative did not exist, and check that those values are within the interval that we're interested in. We found x is equal to 1 was the only one. All right, that satisfied all those criteria. So we've tested, we checked f of 0, and we got f of 0 is equal to 0. We checked f of 3, and got f of 3 is equal to 3/7. Okay? Now we have to check out what f of the critical number is. Okay? So check f of 1. So f of 1 is equal to 1 over 1 squared minus 1 plus 1. That's 1 over 1 minus 1 plus 1, right? Which is just equal to 1. Okay? So we have f of 1 is equal to 1. Okay? F of 0 is equal to 0. Right? F of 1 is equal to 1. And the other one was, at the end point, f of 3 is equal to 3/7. Okay? By the closed interval method, therefore, the largest of these three y values is the absolute maximum on that interval, and the smallest of these is the absolute minimum. And of these three numbers, 0 is the smallest, 1 is the largest. So by the closed interval method, okay, we have that 0, that's f of 0, which gave us 0, okay? The smallest of these three is the absolute minimum, okay, the absolute minimum of f on the closed interval 0 to 3. And the largest of 3 is 1. So by the closed interval method, f of 1 is equal to 1 is the absolute maximum of f on the closed interval 0 to 3. So there's our conclusion then. All right, so a lot of work went into developing this technique. And we did not do this graphically like we were doing earlier, right? We did this entirely symbolically, right? Using the theorems of the section as well as our previous knowledge from calculus and how to solve things like rational equations, right? Even a quadratic equation we had to solve here, right? We used the closed interval method. We had a function that was continuous on a closed interval. And so therefore, to find the absolute max and absolute min that were guaranteed to exist, we had to test at the y values at the endpoints of the interval and the y values at any critical number within the interval. As we discovered geometrically earlier why that had to be so. To find the critical numbers, we need the derivative of the function. We set the derivative equal to 0 to solve for all the values of x. And then we check to see where the derivative did not exist to find all potential values of x. We then compare those values that we find, if any, we compare those to the domain of interest. In the previous exercise, the domain of interest, right, on the trigonometric one, there are a lot of values to exclude. On this one, the domain of interest was the closed interval 0 to 3. So when we found our potential critical numbers, in this case 1 and -1, we only took the 1 because it was the only one that was in the interval of interest. What did we do with the critical number? We found the y value for that and compared it to the y values at the endpoints. That was our list of potential max and min values on the closed interval. The largest of them was the absolute max, therefore, and the smallest was the absolute min. Okay. All right, so you have also here in addition to your typed notes, you have a worksheet and including some solutions there. Okay, find the critical numbers, determine absolute max and mins of the same functions I give you intervals, okay, to test. And of course the homework, which includes some graphical analysis. Okay, here's a graph. Can you tell me which input values correspond to absolute or local maxima or minima? If you have more than one local max or local min, for instance, more than one, you can list them as a comma separated list. It is possible to have more than one local max or more than one local min, but it would not be possible to have more than one absolute max or absolute min. Okay? It's also possible for any of these things to not exist. So you have some graphical ones, okay. Sketch the graph of a function that is continuous on a closed interval and has the given properties. Okay, so they give you the 4 here that you can select from. See if you can do this by hand and come up with some possible functions that look like, that have these characteristics. A continuous function on a closed interval. I gave you several examples like that here in the lecture with the notes. Several examples of functions that were continuous on a closed interval, as well as discontinuous on not closed intervals, right? But sketch one that has like an absolute maximum at 5. So 5, right? So the point where the input x value is 5, the associated y value should be the highest y value on the curve and should be included. An absolute min at 2 should be the lowest y value on the curve. A local maximum at 3, so it can't be higher than the value at 5. But it must be a value whereby either the derivative is equal to 0, so horizontal tangent line, or the derivative doesn't exist. Consider like a corner or a cusp, for instance, could be a possibility. Local minima, 2 of them at 2 and 4. So which one would it be? Right? You can do it by, I want you to sketch that on paper. But if you're doing it by like a process of elimination here, right? At 5, we're only on the interval from 1 to 5. At 5, we should have an absolute maximum. That doesn't look like a maximum. This one's not even existing at 5. This one doesn't exist at 5. Well, this one does, and it looks like that is the absolute maximum right there. Right. Absolute minimum at 2. This point right here, that is the lowest point of all points, okay, on this curve defined on that closed interval. Local max at 3. At 3, we have within a little neighborhood here, that is the highest point, right? It is the highest point on this hilltop, okay? And also, I mentioned that it looks like it's smooth here, so this particular one, it happens to have a horizontal tangent line. You could have sketched a curve where that was a corner right there, and it still would have been a local maximum. And it's not higher than this, so it is not the absolute maximum. It is possible for a point to be both local and absolute max, by the way, right? But we already knew the absolute was at 5. The local minima at 2 and 4. So if we look at 2 and we look at 4, we see that there's 2 minima. Notice that the local minimum at 2 also was an absolute minimum, as it turns out for this particular example. Okay? All right, so construction of graphs with different graphs of different features. Can you sketch the graph of a function with a local max at 8 that is not continuous at 8? How is that possible? That it has a local maximum? That means it must exist to the left and the right of x is equal to 8, but it's not allowed to be continuous. So it's not going to be smooth, right? It's not going to be continuous. There's going to be some kind of discontinuity. Is this it? Well, this can't be it. Why? Because it doesn't have a maximum at 8. Right? Okay. Is it this one? Is that a maximum right there? Is it a local maximum? Okay. And furthermore, is the function continuous here? And is that the value 8? Okay. Okay. Is this a local maximum right here? Is this function continuous there, or is it not continuous? It's not continuous. Is it a local maximum? Okay. Which one is the correct graph? Can you sketch a graph on your own that would have these characteristics on it? Okay. And then you'll have some examples, all right, sketch by hand, a given function on some domain. Notice this is not a closed interval here. All right, you're not using a closed interval method, therefore, to do any testing here. It's not symbolic. You'll use the graph instead. Sketch the graph over this given domain, and using your graph, establish if you have any of these and what they may be. If any of them don't exist, right, it does not exist. Okay, piecewise function, that looks familiar, right, from the lecture. Finding critical numbers. Here's some functions. Can you find their critical numbers? Remember how to find the derivative of an absolute value function? Remember how to find the derivative of a piecewise function? That was a hint, right? Critical numbers. Trigonometric functions. You'll have to solve some trigonometric equations. Okay, let me know if you need any help. Okay, office hours. Logarithmic equation, right? Okay. Absolute max and min. Oh, look what you have. You have a function with a closed interval. What do you think you're going to have to do? Check to see if it's continuous on the closed interval. If it is continuous on that closed interval, guess what? Then these quantities must exist. Okay? We'll work on the constructions of the graphs of these types of functions at a later time. We're not doing this graphically here. You should be doing this entirely by use of calculus and algebra technique, okay? Symbolically finding the absolute max and absolute min by the closed interval method. Here's one with trigonometric functions in it again. And a couple of word problems there, all right, to finish off the assignment. Okay, that's it for this section. There's a lot of stuff here, a lot of practice, okay? As we continue to move ahead, we're continuing to apply the derivative, okay? Let me know if you have any questions. Take care.